Hello everyone, my name is Pankojne Das. I'm a student of MSc and the topic of my presentation is instrumentations of gas chromatography. First of all, let us know what is chromatography. Chromatography is a laboratory technique for the separation of the mixture. The mixture is dissolved in a fluid called the mobile phase, which carries it through a system on which is fixed a material called the stationary phase. This is important for this separation of DNA, protein, different chemical molecules, so that each substance can be studied thoroughly. Let me zoom in this diagram so that the instrumentations of GC can be seen properly. It comprises of gas tank where the temperature rises, where the pressure is about 40 to 80 psi. Then the gas tube, uh, after that, which goes to the GC oven, that is the column oven, where the temperature can be optimized up to 400 degrees Celsius. Then is the sample inlet or the syringe from where the sample is injected. Then comes the GC column, which can be of two types, that is capillary column and packed column. Capillary column is widely used, which is then connected to the detector. After the detector, it is connected to the recorder, where after that it is connected to the electrometer or bridge, then ADC, and after that the data system. I'll be explaining about each of them in the coming slide. So let's get started. Let's talk about types of GC. Gas solid chromatography, that is GSC. The stationary phase in this is a solid. It is the affinity of the solutes toward adsorption onto the stationary phase which determines in part the retention time. The mobile phase is of course a suitable carrier gas. This gas chromatographic technique is most useful for the separation of the analysis of gases like CH4, CO2, CO, etc. Gas liquid chromatography. The stationary phase is a liquid with very low volatility, while the mobile phase is a suitable carrier gas. GLC is the most widely used technique for the separation of volatile species. Carrier gas. A carrier gas should have the following properties. It should be highly pure, inert, higher density, compatible with the detector, cheap and available. The carrier gas pressure ranges from 10 to 50 psi. Depending on the column dimensions, flow rates from 1 to 150 milliliter per minute are reported. Conventional analytical columns usually use flow rates in the range from 20 to 50 milliliter per minute, while capillary column use flow rates from 1 to 5 milliliter per minute. Commonly used gases include nitrogen, helium, argon, and carbon dioxide. Sample injection system. Septum type injectors are most common. These are composed of a glass tube where vaporization of the sample takes place. The sample is introduced into the injector through a self-sealing silicone rubber septum. The carrier gas flows through the injector carrying vaporized solutes. The temperature of the injector should be adjusted so that flash vaporization of all solute occurs. If the temperature of the injector is not high enough, at least 50 degrees above highest boiling component, band broadening will take place. Automatic sampler. Sample vials are glass, throw-away types with vapor-tight septum caps. The sampler flushes the syringe with new sample to remove traces of previous sample, pumps new sample to wet the syringe to remove any bubbles, take in a precisely measured sample and pumps into the gas chromatograph. Headspace technique. It involves analysis of volatile components in a complex and viscous mixture containing high proportions of non-volatile components. For quantitative analysis, calibrations of the volatiles in the vapor is necessary. To reach this site, the sample is placed in a glass vial and thermostated. When equilibrium is achieved, an aliquot of the gas phase above the sample is rapidly transferred onto the GC column. All the devices that are commonly used for the gas sampling may be applied to the headspace analysis, including gas-tight syringes and gas sampling valves. This is a diagrammatic representation of headspace technique. Now let's talk about columns. The column in chromatography is undoubtedly the heart of the technique. A column can either be packed or tubular. Let's discuss each of them thoroughly. Packed column. These columns are fabricated with glass, stainless steels, copper or other suitable tubes. Stainless steel is the most widely used because it is most inert and easy to work with. The column diameters currently in use are ordinary 1 by 16 to 1 by 4 OD. Column exceeding 1 by 8 are usually used for preparative works, while the 1 by 8 or narrower column have excellent working properties and yield excellent results in the analytical range. Column length can be from few feet for packed columns to more than 100 feet for capillary columns. Open, open tubular capillary columns. Open tubular or capillary columns are finding broad application. These are mainly of two types: wall coated open tubular, that is WCOT, which is less than 1 millimeter thick liquid coating on inside of silica tubes. Support coated open tubular, SCOT, 30 millimeter thick coating of liquid coated support of inside of silica tube. The most frequently used capillary column nowadays is the fused silica open tubular column, which is a wall coated open tubular column. The external surface of the fused silica column is coated with a polyimide film to increase their strength. Support materials and stationary phases. The solid support should ideally have large surface area, has a good mechanical stability, thermally stable, inert surface in order to simplify retentions behavior and prevent solute adsorption, has a particle size in the range from 100 to 400 millimeter. Example: diatomeous earth, glass beads and suitable mash size. In general, the polarity of the stationary phase should match that of the sample constituents. Most stationary phases are based on polydimethylsiloxane or polyethylene glycol backbones. These are the diagrams. Temperature programming. Gas chromatography are usually capable of performing what is known as temperature programming as gas chromatography, TPGC. TPGC is a very important procedure which is used for the attainment of excellent looking chromatograms in the least time possible. Thermal, isothermal, keep oven at one temperature through run, or then possibly useful for series of very similar compounds differing by boiling points such as alcohols. Gradients temperature profile: 40-degree holds for 10 minutes, then 10 degree per minute to 240 degree and hold there for 20 minutes. Several detectors are available for the use in GC. Each detector has its own characteristics and features as well as drawbacks. Properties of ideal detectors include high sensitivity, minimum drift, wide dynamic ranges, operational temperature up to 400 degrees Celsius, fast response time, same response for factors for all solutes, good reliability, non-destructive, and response to all solute, that is, it should be universal. Now let's discuss about some of the common GC detectors. Flame ionization detector, FID. Mass sensitive detectors response depends on conducting power of ion or electrons produced on burning of organic compounds in the flame. Selective detectors, but sample detected must be combustible, large aligner, dynamic ranges, no response to inorganic and permanent gases such as CO, CO2, NH3, CS2, N2, etc. It is most widely used detector in gas chromatography. Thermal conductive detector, that is TCD, non-destructive universal detector. Response depends on the thermal conductivity difference between the carrier gas and the elated components. Wide dynamic ranges. Responds also to inorganic gases such as CO, CO2, NH3, CS2, N2, etc. Sample is not wasted and easy to operate. Now let's study about the last electron capture detector, that is the ECD. ECD ionizes the carrier gas by means of radioactive sources. The potential across two electrodes is adjusted to collect all the ions, and a steady stereations current in therefore recorded. Electrons from beta sources ionizes carrier molecule, capture electrons and decrease currents. Simple and reliable. Sensitive to electronegative groups, halogen, peroxides, largely non-destructive, insensitive to amines, alcohols and hydrocarbons. Limited dynamic ranges. So that's the end of the presentation. Thank you and have a nice day.